Okay, today we are very pleased to have Dr. Dominique Segura-Cox as our Astro Colloquium speaker. So Dom is a proud alumnus of our astronomy PhD program. So after obtaining her PhD in 2017, she joined the astrochemistry group at the Max Planck Institute for Extraterrestrial Physics in Germany as a postdoctoral fellow and has been there since. And I learned this afternoon that she's coming back to the US this fall and will be a NASA postdoctoral fellow at UT Austin. So congratulations, Dom.
Thanks.
So Dom is an expert on protoplanetary disks and protostellar environments. So she uses high-resolution interferometric observations to take stunning images and spectroscopy of protoplanetary disks to understand the formation of young stars and planetary systems. Today, she will tell us about her latest excitements on these topics. So please take it away, Dom.
Great, thanks a lot. So today I'm really excited to talk about a lot of my work that's focusing on this particular protostellar system that I have on my title slide, and it's called IRS-63. And it's a class 1 protostar, which is a bit younger than the typical protoplanetary disk that we would normally think of. And I've been studying it in such detail because it has these rings, and it's some of the youngest examples of rings that we have in a disk. And I'm excited about the rings because rings are very favorable environments for planet formation. So the rings can help to overcome the radial drift problem, which is a really severe planet formation barrier. Essentially, the radial drift causes disk material to flow inwards and be accreted by the central protostar that happens on timescales that are typically too short to allow for dust to grow into planetesimals based on the current modeling that we have. So rings might actually be a solution to this by providing a stable radial zone where the infalling material is slowed, and that allows dust to pile up into these denser rings, and they can be present for long enough periods of time that allows for larger planetesimals to grow. And in particular, some of my in-prep work is showing us that this particular protostar is even more interesting to study because while it does have these beautiful young rings, the disk itself is also still accreting material from a larger envelope through this asymmetric accretion streamer that we have here. So that's implying that the disk material that's being consumed by the central protostar or perhaps locked up into planets at this early stage is being replenished by material from the envelope. And it's sort of an indication that stars and planets begin to form and evolve together from earlier times in the star formation process than we've previously considered. So just a quick recap of our current view of star and planet formation is in the very early years, we have a prestellar core, which is typically 10,000 AU or larger across. We sort of have assumed that they're roughly spherical and they're dense enough that they can have this gravitational infall. And then by the class 0 and 1 protostellar phase, which is what I focus on and study, you start to have the disk that will form, and it also has this sort of infalling envelope. And until some of my recent work that I'll be showing here, we sort of assume that this disk has been roughly smooth. Then later by the class 2 phase, when you have most of the envelope already accreted onto the central protostar or dispersed by the outflows, you can still have a little bit of these envelope remnants that continue to infall, but most of the envelope has been depleted. And in this phase, we've also had a lot of evidence now that there are already rings present in these disks. So that's not disputable anymore. We know that that's for sure. And then finally, after about 10 to the 7 years, you'll have a star and planet system that's similar to what we live in now. I'll sort of be discussing some of the changes we might actually have to be making to this general view of star and planet formation based on some of the work I'm currently doing. So again, of course, we know at this point that rings are found in nearly every disk in the class 2 phase, which are in systems that are older than about 1 million years old. So these are the beautiful rings from the D-sharp program. And we also saw the first indication of this, of course, from the famous HL Tau image that was released in 2015. So we've had about half a decade of work in the more evolved class 2 phase when there's no longer an envelope to study these ring systems. So the rings and gaps that are so clear in these images are often interpreted as indirect signs of ongoing planet formation. And it's clear from these images that if planets are shepherding the disk material into these sharp rings, then the planet formation process has to have been going on for quite some time. I mean, for a planet to have such an influence on the disk structure to really carve out the material and to make these really clear rings, it must have had enough time for the planet to gain significant mass. And that sort of brings me to my question, which is, when do these rings actually start to form? If they're already present in the class 2 phase, are they also already present in the class 0 or class 1 phases? Or do they rather quickly evolve towards the beginning of the class 2 phase? But before we start to search for rings in embedded disks, I think we first have to understand some basic properties of disks themselves. So only recently have embedded disks been able to be studied in detail with sensitive sub-arc second interferometric observations that spatially filter out a lot of the surrounding envelope emission. And it's important that we target these in the millimeter and radio wavelengths so that we can actually have a detectable disk. Otherwise, we'll just be detecting the surrounding envelope structure. So first off, to form rings similar to those we see in class 2 systems, the young embedded disks must be similar in size to older disks. And that's what we have here on the left. So this is part of my PhD thesis work that I did at UIUC with the VLA Nascent Disk and Multiplicity Survey that was led by John Tobin, another UIUC alum. He was there as an undergrad. So this survey, shortened to the Van Dam survey, surveyed all class 0 and 1 protostars in the Perseus molecular cloud with 15 AU resolution. And it was the first survey to have a statistically complete sample of all the protostars in a molecular cloud with such high resolution and to actually be able to talk about this statistics. In the embedded phases. Again, this is for the class 0 and class 1 stages when there's still a large envelope. So we found that roughly 20% of the protostars had disks that are larger than 15 AU. And we also consider these to be lower limits on the true dust disk radii because larger grains that are traced by the centimeter VLA wavelengths are likely more centrally concentrated than smaller dust grains that are more readily traced by millimeter wavelengths with ALMA. But nevertheless, this has showed us that it's not rare for disks in the embedded stage to be large enough to encompass Neptune orbits and beyond. Also, if these disks are going to be the future sites of planet formation, then we have to think about the mass in the disks. There must be enough mass in the disk to actually form a planet. So here on the right is work by Lucas Tikoniak. And just this year, he found that the mass reservoir that's in the embedded disk can explain the typical distribution of exoplanet masses. But the class 2 disks don't seem to have enough observable mass to explain the mass that we see in the exoplanets. So the exoplanet masses are marked by the gray points, and the average disk masses of the class 2, class 1, and class 0 protostellar disks are marked by the dashed lines. So we see that the class 2 disks just don't seem to have enough mass to explain what's going on with the exoplanets typically. However, the class 0 and the class 1 disks do. So it could be that by the class 2 phase, there's already significant mass that's locked up in planets and not observable with millimeter interferometers. And that's hinting that planets must start to form earlier in the class 0 or class 1 stages. So now we've established that there are some basic conditions that disks need in order to form planets, and those seem to be met in the embedded stages of star formation before the more well-studied class 2 phase. And it's clear that the mass is available to build planets at solar system-like planet radii early on, but the question I seek to answer is, do the rings actually form in the stage? So because rings provide a way to keep the dust at planet-like radii for long enough time for a planet core to grow, rings also likely represent a third required initial condition for solar system-like planet formation to start to occur. So to find the earliest signs of planet-forming rings, we first need to study a large disk in detail in the embedded stage of star formation. And I targeted this source, IRS-63. It's a bright class 1 protostar that's on the outskirts of the Ophiuchus molecular cloud, and it's relatively isolated. There's no other source near it within 2 arc minutes, and the source that's 2 arc minutes away is likely some sort of pre-stellar condensation. And unlike the older disks, like the HL tau or D sharp disks, it's still highly, highly embedded in its envelope. So I targeted it with ALMA 1.3 millimeter observations that had 5 AU resolution to determine if it was possible for rings to exist in the class 2 phase. And the observations were basically designed to mimic the ALMA science verification of the famous HL tau image that initially showed us that the disks around protostars that are about 1 million years old had rings. Now, IRS-63 is much younger than HL tau, and it's about 1.5 to 500,000 years old. So it's at least half the age of HL tau. And this is the data. And on first inspection, it looks relatively smooth. So that's quite unlike the D sharp disks or HL tau that we saw previously from the older class 2 stage. However, the issue we have here is that the central protostar is so bright that the data is really highly dynamic range limited. So we have to do some data processing tricks to really tease out the structure of the disk. And one of those is by using enhanced contrast imaging techniques. So,
hey Dom, sorry for interrupting, but could you perhaps remind us real quick, what the age uncertainty is driven by? So the age is determined from the temperature.
Right. The age tends to be driven by the bolometric temperature, because in the class 0 and class 1 phases, we don't actually have a spectral type yet. So we can't rely on spectral typing like in the class 2 phases to try to get a handle on the age. And the measurements of the bolometric temperature can be uncertain. And the current modeling we have for connecting the bolometric temperature to the age can also be somewhat uncertain. So that's why there's this rather large uncertainty here. So I would say that this is actually encompassing the true age somewhere in there of IRS-63, although I can't say with certainty exactly where it would fall.
Thank you.
So if we apply an enhanced contrast imaging technique to the data, what we can do is filter out some of the emission from the larger scale underlying dust disk, and it shows regions of overdensity. And we see that there does appear to be a pair of bright rings, R1 and R2, and slightly dimmer gaps, G1 and G2, that are at constant radii throughout the disk. So the structure of this disk likely has an impact on planet evolution starting early in the star formation process. But I don't want to rely on just manipulating the images with this enhanced contrast imaging technique. So with my colleague Annika Schmiedeke, we also tried to check for the rings with the radiative transfer model. So our idea was not to perfectly reproduce the structure of the disk of IRS-63, but instead we wanted to make a relatively realistic model of a smooth disk with RADMC 3D that's heated by the central protostar, and then subtract that from the dust continuum image. And then that gives us a residual image. And we also see here that indeed the gaps G1 and G2 and the brighter rings R1 and R2 are reproduced at exactly the same radius. So 2 different techniques to really show off these low surface brightness details that are in the disk. And we've been able to overcome the dynamic range issue that was present in the data. So now we can move on to the gap and the ring properties. So when we're thinking about the class 2 disk, typically the gap width is an especially important parameter when we're thinking about planet formation. So in Kanagawa et al. 2016, they use hydrodynamic simulations of disks with planets in them to provide us with an empirical relation of gap width to planet mass relation. So if we assume that each gap, G1 and G2, is opened by a single planet each, then in this disk, planets of up to 0.3 or 0.5 Jupiter masses might be present. Now, to me, these are really surprisingly large planet masses at these large radii, and for such a young disk that's less than 500,000 years old. So considering that the earliest stages of planet formation face serious barriers to even grow to a large mass on this short time scale, and then once we have a planet core mass that's something that's as large as 0.5 or 0.3 Jupiter masses, we also have to worry about how to stop the runaway accretion of gas at later stages. To me, if these are accurate, then that would imply that the runaway process that would happen, the runaway gas accretion process that would happen at later stages might actually turn these possible planets into brown dwarfs. So I just like to caution that in reality, these values are actually super strict upper limits. For instance, if we're not resolving the gaps perfectly with our 5 AU beam, for instance, if they're only 2 AU in width, then this method will really severely overestimate the planet masses. And I'd also caution that this empirical relation between the gap width and the planet mass was also developed with disk properties that are more common for the more involved class 2 stage. So because class 0 and class 1 disks are embedded in their larger envelope and they're still feeding from the larger scales, it's not necessarily true that the typical disk parameters of class 0 and class 1 sources would be the same as the disk parameters of a class 2 source. But nevertheless, having these extreme upper limits on the planet masses is important to keep in mind when we're thinking about planet formation models.
Dominique, can I ask a question?
Sure.
So if you're trying to use the gap width to work out the planet mass, doesn't that require some degree of time integration, right? So won't the planet clear out a larger gap over time, or is it not a secular process the way I'm thinking about it?
Well, I guess as the planet would grow, it would have a larger Hill sphere, so then it would have a larger radius of influence to clear it out. So I think you're right that there is probably some time aspect to this, but that's also why I caution that these are super high upper limits. I think you bring up another good point of why we shouldn't trust these.
But this relation with the width and the mass is really kind of a Hill type sphere, not a Hill type radius. It's not something that comes out of a numerical simulation necessarily, or is it a little bit of both?
It's a little bit of a both. So it takes into account some of these. So the gap width planet mass relation that we used here and that's commonly used for the class 2 system does come from statistics from numerical simulations. But by playing around with some of the parameters, you can then relate the width back to the planet mass relation that does involve the Hill sphere. So it's a bit of a combination.
Yeah, okay. Fair enough, thanks.
But this actually brings me to my point that I think personally, it's actually much more interesting that in the case of this class 1 disk, we should be taking the conservative assumption that large planet embryos have not yet formed and they're just beginning to grow in the rings. So this will probably be the last time that I actually mention gaps, because I think in the embedded stages, the rings are actually where the more important science is happening. And I think that's partially because the rings might represent the first overdensities where planet formation may be able to get a foothold for future planet growth. So focusing now on the rings, The rings that we have here are actually wider and lower contrast compared to the rings in the older disks. For instance, the ones that we saw in the ALMA D-sharp large program. So this might be telling us that these young rings are actually fundamentally different than the rings in the older disks. So if the older disks are being carved by planets, these might be rings that are being formed by some other mechanism. Also, if planets haven't even formed in this disk yet, and we're still seeing the forming rings, which will eventually reach dust to gas ratios that are favorable to trigger the streaming instability, which can form the first generation of planets, then that might imply that the first generation of planets could shepherd the dust into the sharp rings by the older class 2 stage. So what we're seeing now is not fully formed embryos, but in the rings, they will eventually form sizable planets so that by the time you get to the class 2 stage, the planets have gained enough mass to actually make those sharply defined rings. And that might be why we're seeing such different properties, such as the lower contrast and the wider width here compared to the class 2 rings. So it could be that these are just the first generations of rings in a disk, and then this D-sharp rings are actually a second generation of rings that are sculpted by the first generation of planets forming in the rings we see here. And I also want to emphasize that the disk of IRS-63 corresponds quite nicely to the size scale of our own solar system. So here I plotted the solar system with the same inclination and size scale as the IRS-63 disk. And I'd like to point out that both these rings here and here are actually much larger than the orbit of Jupiter, which is represented by the little orange ellipse here. And what we also found is that by converting the flux to mass, there's about half a Jupiter mass of solid material exterior to the first gap. So half a Jupiter mass of material in these two rings. So that's implying that there's enough solid material in the outer part of the disk to form multiple giant planet cores that can later undergo runaway gas accretion and potentially form something like a planet. And that's also consistent with recent building evidence from pebble accretion models, asymmetries and dynamics of the Trojan asteroids around Jupiter, and astrochemical arguments that Jupiter's core might have formed beyond 30 AU in our own solar system, perhaps in the vicinity of where we see rings in this class 1 disk, and then later migrated inward to where it currently sits. So the disk of IRS-63 may very well be like a young solar system analog and a window into the first steps of assembling planets like the ones we see in our own solar system. So that gets me to the point of how are these rings actually forming if we don't yet have sizable planets? So some ideas being thrown around right now are there could be hidden planets that are still forming on younger timescales that we don't know about, or there could be magnetorotational instabilities that can cause material to pile up into rings due to pressure traps. And essentially, the gas in the disk will wind up forming these pressure gradients that we see here that make these stripy bands, and material will converge in these particular areas due to the magnetorotational instabilities. It could also be that disk winds in unevenly ionized disks may be able to cause sort of ring-like structures. This is based on simulations. And another idea that's starting to gain traction is that you could also have self-induced dust traps. So a lot of simulations currently are taking into account the dynamic interaction of the gas on the dust, but it doesn't also take into consideration the effect that the dust has on the dynamics of the gas. So if you're taking into account only the dynamics of the gas on the dust, in the bottom here, you don't actually see rings start to form. But if you do take into account that the dust should in turn affect the gas, and you're looking at the dynamics going in both directions in the top, you can actually form multiple rings where these, where you can have denser areas of material start to form. And that can happen in a perfectly smooth disk, and you don't need to have uneven ionization. So I think that's something we need to keep in mind. And another potential ring formation mechanism that I'm especially interested in is the CO Snowline. So snowlines represent a radius where in the disk, the temperature drops and becomes cold enough for an icy layer of some volatile material to freeze out from gas into the ice phase. And then this icy layer will form on the surface of a grain. So that can also help with grain growth, because now that you have the sticky icy layer on top of the dust grain, it's easier for collisions between dust grains to actually form, to actually stick instead of bouncing off of each other. So if they can stick together more easily, you can build larger grains faster in these regions of the disk. So based on using the continuum data that I had for IRS-63, the IRS-63 disk, I found that the position of the CO Snowline based on the temperature, which is in this pink zone, highlighted in the center of the graph, seems to be in agreement with the CO Snowline, because the spectral index on top is increasing across one of the gaps, while the optical depth is decreasing. And from modeling of the behavior of dust around CO snowlines, well, snowlines in general, water snowlines should also have this effect, or NH3 snowlines. Any snowline should have this effect, where you have the spectral increase, the spectral index increases across a gap while the optical depth decreases. So this is sort of tantalizing evidence that at least one of the features in this disk might be connected to a snowline. So that brings me to the question of, do these snowlines matter early? So snowlines have been studied in detail for class 2 disks. And for class 2 systems, it seems like the rings and the snowlines are not often linked. So for instance, they've done this analysis trying to look at where these, where the CO snowline should fall based on the temperature, expected temperature of the disk, and compared those to the actual ring radii of the D-sharp disks, and they actually didn't find a correlation between those. However, if you use chemical tracers of the CO snowline, such as N2H+, sometimes there's a connection. Not universal in all class 2 systems, but sometimes. So we use N2H+ as a tracer of the CO snowline because N2H+ is destroyed where CO is in the gas phase. So that would be in the center here where the disk is hotter near the protostar. And if however, outside of that region, N2H+ is present, then CO is in an icy layer on dust grains. So then they can become more sticky. So for IRS-63, I'm starting to assemble this, and I've actually have a detection of N2H+ at significantly lower resolution than I proposed for. This observation was actually supposed to be a companion compact array compared to the 15 AU data I wanted. I got roughly 100 AU data instead only. And I wanted the different size scales to be traced because I wasn't sure how sensitive I needed to be on the larger scales. Because as you can see from the class 2 disk, the N2H+ doesn't actually disappear as you get to larger and larger disk radii. And that's because it should still be cold in that outer part of the disk. It's just an issue of sensitivity and whether or not you can actually detect it out here. But N2H+ should also be present out into the envelope in the class 1 phase as well. So if we zoom in on mine, these two blue lines are actually showing us where from the dust continuum temperature map, somewhere between these two blue lines is where the CO Snowline should form, or where the CO Snowline should be. And the fact that we see the inner edge of the N2H plus really close to these radii is maybe telling us that the temperature that I had originally measured with the continuum data only might actually be somewhat, might be pretty accurate, because in here it's too hot for the CO to be in the ice. Instead it's in the gas, so the CO is destroying it. And then exterior to that, the disk is cool enough that we can have CO being the icy phase, and then the N2H plus appears. So again, just tentative evidence that maybe there's a link in IRS 63 for one of the features to be associated with the CO Snowline. On the other hand, unlike in the class 2 systems, we don't really have a lot of material extending to larger scales. And in fact, the N2H plus sort of ends at a rather sharp truncation radius. And it doesn't seem to be an issue of sensitivity. There just isn't actually a lot of N2H plus out here. And in this system, the N2H plus is really like a ring. And that would actually imply that in the exterior part of the disk, it becomes hot again, so that the CO is back in the gas phase. But it's unclear what's actually causing, just from this data alone, it's unclear why the disk would heat back up. You would need to have some sort of exterior source of heating to explain that. And I think that's where the envelope is coming in. So we of course know that not only do we have the temperature tracer of the N2H plus in this data set, we also had H13CO plus, which is a lower density tracer, or sorry, a higher density tracer. I think this traces something like 10 to the 6 in number density. And this is sensitive to material that's not only in the outer part of the disk, but it's also sensitive to material in the envelope. And this was completely unexpected. We didn't actually expect to see that there's this stream of material that's leading up to larger scales that's surrounding this. And then if we actually look in the velocity structure of the disk, we see that there's a smooth velocity gradient that's approaching from large scales, roughly around 1500 AU away from the central protostar, approaching the disk, and then it joins smoothly with the blue shifted side of the disk down here. And this smooth connection is also roughly at the radius where the N2H plus disappears again. So it could be that heating from accretion from the larger scales can heat the outer part of the disk so that the N2H plus disappears again. So it could be evidence that in the embedded stages, not only could snowlines matter for creating the first generation of rings, that another telltale indicator of accretion from envelope to disk mattering in the younger stages could be if we find sharply defined N2H plus rings, the outer part could be evident. The outer part of the N2H plus being so sharply defined and not just smoothly tapering off into the envelope is evidence of ongoing accretion heating the outer part of the disk. And what's interesting is we can also come up with a streamline model that explains how a parcel of material that is present in the core would fall inwards towards the central protostar. So this is using a streamline model from a rotating and collapsing core, and it traces the trajectory of material not only in the spatial structure, which we see here on the left, but it can also give us a description of what the velocity structure should look like, which is what we see on the right. And the agreement between the agreement of the model and the fact that it can explain both the spatial structure and the velocity structure is really tantalizing evidence that we really are seeing a clear funnel or a clear avenue of accretion from envelope to disk. And it's completely asymmetric. We didn't expect that, but it's exciting. And this is not the only streamline, or this is not the only accretion streamer where we found that the streamline type of modeling works. So this has also been found in a class 0 protostar. This is using a different tracer. This is HC3N, whereas in the previous IRS-63 streamer, I found the streamer in H13CO+. But here again, we also have this sort of streamer that's explained both in velocity, or sorry, in spatial and velocity structure by a streamline model. So this might be actually a reliable way to identify more streamers. And now that we're finding more streamers, we can start to think about how would streamers evolve with time as the protostar ages. So I think one interesting thing to compare is how large are the streamers. So from the data we have now, there's not a lot of data that's been collected on streamers, but the data we do have has been serendipitously detected. So we have 3 clear examples in the class 0, class 1, and class 2 phases, but they're all in different tracers. So we have HC3N, we have H13CO+, 4 to 3, and we have HCO+, 3 to 2. So the question then becomes, what is a reliable way to actually, or what's a reliable molecular line, molecular tracer of these structures? We don't know, because these programs were all designed to achieve different goals. We weren't looking for streamers with any of these studies. We just found them on accident. So for the class 0 system, we were actually trying to look for tracers of envelope material because we wanted to understand the angular momentum profile of the core to disk scales and understand how that might change and how the specific angular momentum might change as material is approaching the disk. For my IRS-63 data, the original goal was to find evidence of an association between the ring structures and the CO Snowline. And for HL tau, which we know has those beautiful sharply defined rings, the original goal was actually to understand whether or not there could be pressure traps in the disk that might be contributing to why there could be these densities in the rings like piling up. So disk dynamics, disk chemistry, and envelope rotation all led us to finding these streamers completely by accident. And they're all on very different size scales. So in the class 0 phase, it's a 10,000 AU streamer. In the class 1 phase, it's a 1,500 AU streamer. And in the class 2 phase, it's a 150 AU streamer. These are all very different size scales. And that might make sense if we take into account that in the class 0 phase, you should have a lot more material in the envelope. It becomes a bit more dissipated by the class 1 stage, and then by the class 2 stage, there's almost no envelope material left to be accreted in either by spherical infall or by a streamer. So I plot these here all with the different scale bars, but what kind of blew my mind about how different these size scales really were when I plot them all on the same physical size scale. I mean, these are just massive differences in the size scales where we see streamers, and they can all be explained by the Streamline model. It all makes sense that this is material that's accreting along a streamline from a rotating collapsing core, and that eventually winds up into the disk. And we can explain it with stuff that's starting to reach core scales, stuff that's clearly the envelope, and stuff that's mostly just the leftover last bits of stuff accreting into the disk. And I'd also caution that we don't actually know, for at least the IRS-63 data, how far these streamers actually go. So on the right here, I have the Herschel column density map, and the IRS-63 streamer data I've actually plotted as contours here. And the little dashed circle is actually the primary beam of the ALMA observations. So because this is an interferometer, the sensitivity of the instrument drops off outside of the primary beam. And as you can see here, the streamer ends somewhat, I don't know whether to say conveniently or suspiciously, right at the primary beam of the observations. So there's a hint that this streamer might actually be going further and be much larger than we currently understand. And indeed, the streamer is actually pointing towards a sort of overdensity in the Herschel column density map, where there might actually be a larger reservoir of material to be accreting from. So tonight, my colleague Anna Kosmiedika is actually doing observations for me with the ERAM 30-meter dish, which will uniformly cover everything in the circle here. So then we'll be able to understand exactly how far the H13CO plus might be tracing the streamer to larger size scales, or not, we're not sure. And we targeted this size scale because if I plot the class 0 and the class 1 streamers on the same size scales, physical size scales, these are both 5,000 AU scale bars now, we see that we will actually be encompassing the primary beam of the observations that we had for the class 0 source. But same story we had with the class 1 source, we also have with the class 0 source, so that the streamer seems to end suspiciously right at the end of the primary beam. So even that protostar might be accreting from larger scales than we're currently sensitive to. And there's also more follow-up work that'll be done with single dish instruments on that as well. So we still don't have an answer to the question of how far they would go, which is also why we're not sure if streamer sizes evolve with time or not, or if they're just constantly accreting from huge size scales until almost to the end of the core dissipation phase. And streamers seem to be becoming the new normal. So I already gave you 3 examples of observations that we saw, which were the class 0 and the class 1s that I was just talking about, and HL Tau had its own streamer. And recently, Felipe Alves has also found another pair of streamers actually here and here towards another class 1/2 source, which is more like the age of HL Tau at about 1 million years. But I just wanted to highlight the fact that streamers were actually predicted by simulations before we even had the observational data in hand, and from different flavors of simulations as well. So the simulations by Michael Kufmeier were actually designed to study how cores might, how material might accrete from core scales during the course of binary formation. So there's actually a binary protostar forming in here. And it looks remarkably similar to the data that we have for the class 0 streamer. And what's interesting about this source is that there's also a type binary that's forming down here. It's not a single source. All of these other ones are single sources, but this one has a binary source, and it has this sort of chaotic, somewhat more chaotic features that's also seen in the simulations. And the simulation wasn't made to specifically reproduce this source. We just happened to see it, and it's really, I don't know, it's really tasty evidence that we need to keep looking into these sorts of things to understand if these are common or not. There's also non-ideal MHD simulations by Bo Zhao. He includes magnetic fields. He includes angular momentum in different flavors of angular momentum in the initial core scales. And he includes both large and small dust grain sizes in the simulations. And he also finds that there are like a few hundred AU scale sort of these accretion arms that are occurring, which are more similar to what I see towards my class 1 protostar IRS 63. So all of this is building up to, we're getting this picture of streamers are sort of these envelope to disk or maybe planet scale conveyor belts of material. So anything present in these larger scales here and here, because these are in the class 0 and class 1 phases, might actually wind up in the disk and in planets later. So we could also be thinking about studying like the chemical content of what's going on in the envelope and in the cores to try to understand what might make it into planets later. So I think all of this is adding up to, we have to start to say goodbye to our typical spherical infall model that we always have in our head and in our pictures. And finally, as I said before, everything so far with observations of streamers has been an accident until now. So we have developed a program to start to do statistics of streamers with NOEMA. So NOEMA is a French interferometer. It's something like a cross between the SMA and ALMA. And through the Max Planck Society, we at MPE actually have access to exclusive observing time on the instrument. And with Paolo Caselli and Thomas Henning, we developed the Protégé survey, which is protostars and disks global evolution. And this is a 520-hour survey that will be observed over 4 years. We have the first year and a half of data delivered so far. And it's going to cover 32 class 0-1 protostars and 8 class 2 protostars. And I had a big role in determining what the science goals and the observational setup for the 32 class 0 and class 1 protostars should be. And one of the things I wanted to address was we need to target specific molecules that we saw before could trace these streamers and see what's normal and what's not normal or how common they are. And the good thing about this is that NOEMA is also a broadband interferometer. So we have, unlike ALMA, which has only like narrow observing bands to target molecular lines, this has a huge coverage. So you would have to have, I think, 8 separate ALMA tunings to have the same bandpass coverage that you have with NOEMA in a single tuning. So since we're not actually sure what molecular lines trace the streamer material best, or what critical densities they should be, or what types of molecules, for instance, are ions better tracers or are carbon chains better tracers, we don't know, going the broadband route was best for this. And from the preliminary results delivered so far, which is only about 1/8 of the data, we are finding indeed that streamers keep coming. So for 8 sources where we have partial data delivered, there are strong indications that 5 of the 8 class 0 and class 1 sources might actually have streamers. And this source is one example of them that I'll be working on as an in-prep paper later this year, where there is a bipolar outflow, which are the red and the blue. And we have material that's, we have a molecular line that's tracing the Streamline material with the blue shifted component on this side and the red shifted component this side, but these are the same molecular line. And this is, I think, one of the first times we've actually seen 2 streamers feeding an embedded protostar simultaneously. And just like I was able to do with the IRS-63 streamer, I was able to fit Streamline models to the red shifted and the blue shifted components of this. And the Streamline models, which are in gray here on the map, explain both both spatially and velocity, what's going on with the structure of the molecular line data. And we also have a shock tracer here, just completely by accident, thanks to the broadband coverage of NOEMA. We got the shock tracer that's actually showing that seems to be an extension towards the north of the disk. So the dust disk is roughly here where the black ellipse is. But in the green, it's asymmetric, and there's more of the shock tracer to the north, which is interesting because, as you can see, the landing sites of these streamers are quite different. So the blue shifted component, the blue shifted streamer seems to be landing closer to the dust disk, potentially further in to the disk compared to the red shifted streamer. So that might be telling us, the shock tracer might actually be telling us that just that the blue streamer could be having more of an impact on the disk compared to the red side of the streamer. So I can't go into too many more details than this because it's still super proprietary, but just want to give you a flavor of what's on the horizon. And we're excited that we have 3.5 more years of this data to come. So that brings me to one of my last slides, which is, I think we need to update the star and planet formation schematic. So we have the old, what we thought idea up here, but what we're seeing, especially now with the NOEMA data, that we're seeing that streamers are more common. I think we have to start off by assuming that there's not a spherically symmetric infalling core, but that we have asymmetry starting from the early stages. And that could help explain why we would have asymmetric streamers that start to form and that we can observe in the class 0 and class 1 stages. So no longer do we have a just a spherical infalling envelope. We can have these denser regions where we have infalling streamers. And in addition, my work with the IRS-63 data from my Nature paper is showing us that we do have rings in the disk at very early times. Maybe not planets yet, but the rings are there, which can help to form planets later. Which is also maybe showing us that by the class 2 phase, like we see with HL tau, you might still have just a few remnants of the streamers, in addition to the remnants of the infalling envelope. You still have a ring disk, but this disk might actually hold planets that had started to form in the class 0 and class 1 phase. And then by the end, we do wind up seeing sort of the similar picture of a star and planet system by the end. It's just the process of how it happens and the timescales of planet formation have to be moved sooner. And I think the streamers, if they're common, could actually help explain why we see so many clear ring disks and potential planets in the class 2 phase, because if the material from streamers approaches the disk and then and if angular momentum is conserved as it enters the disk, then it's going to naturally form a ring. And if we're already starting from asymmetric structures on large scales, we could easily imagine that you could have some ring formation from this conservation of angular momentum from the streamers as it enters the disk. If the streamers have are not uniformly dense as material accretes, if instead there's lumps that fall in along the streamers, that might explain why you can have multiple rings at early times. Or in addition to the snowlines, maybe the snowlines can form one ring in the disk and then another ring farther out could be formed by some of the streamers as it's entering the disk. So it's all adding up to this idea that the early phases of star formation matter, and that because we see rings forming the class 1 disks and the disks themselves are still accreting from these large scale streamers from the envelope, then the envelope might actually play a strong role in forming the conditions that can actually make like planet formation really favorable in the class 0 and class 1 stages. So I think especially as we're seeing that more and more streamers are being identified, now that we know what to look for, we have to take into account this envelope to disk to planet conveyor belts of material into account when we're doing future surveys, and maybe start including some of these streamer tracers in future observations, because we need more information, especially as we're seeing them becoming more common. Thanks.
Thank you, Dom, for great talk. I think I see a few hands. Charles?
Yeah, hi Dom. Great talk, thank you. I'm wondering how these things fit into the mass and angular momentum budget of the disk. And especially with the angular momentum, is there enough there that you could actually, well, first, is it misaligned? And is there enough angular momentum there that you could tilt the entire disk?
Yeah, great question. So actually, if I go up here, what's interesting, actually, maybe this one's better. What's interesting is that from the Streamline model, you can also sort of get an angle of approach. So the angle of approach for the streamer here is about, I think, 20 degrees above the plane of the disk. And also the position angle of the dust continuum is not aligned exactly with the position angle of the rotating Keplerian motion that we see on smaller scales. The dust and the Keplerian rotation data seem to be indicating that the gas on larger scales in the disk is misaligned by 10 degrees from the dust in the smaller disk. Now, whether or not there's enough material up there to actually change, to explain that change or to further warp the disk, I'm not sure yet, because we only have the single tracer of the molecular line. So something that I want to do is, in addition to getting, for instance, the 4-to-3 data, I also want to get the 3-to-2 transition. So then I can have 2 transitions and I can start to get an estimate of column density and actually mass budget in that. That's something I want to do in the future. I'm definitely thinking about.
So just one comment. A long time ago, there was a model for the problem of Uranus. So Uranus is tipped over, and the question was how did that come about? And the idea was that you made the planet so that its spin angular momentum was normal to the disk, and then you add material into the disk that tilts the entire disk, and it kind of drags the planet with it as you tilt it. And I don't know if that's viable anymore, but this notion that you can move disks around, move planets around with the disk is an old idea.
Okay, that's great. Yeah, I have to look into that. Thanks.
So Xin, another next question.
Yeah, thank you. Thanks again for a great talk. I particularly enjoyed your cartoon figure that shows the change in the the paradigm that really I think highlights the the progress that this field is making. Is very impressive. So I have a quick question. So for the image that you showed with the contrast enhancement applied, do you, I mean, is there evidence for clumpy structure, or is it some artifacts due to the contrast enhancement? And if it's real, does it help potentially with discriminating between the annular substructure formation mechanisms?
Yeah, that's a great question. So you're talking about this image where you do sort of see some noisiness here.
Yeah, it looks like perhaps it's noise or real.
Yeah. So that's actually, yeah, that is a product of the sensitivity of the data. So there are follow-up observations to go even deeper. That's a part of the ALMA Faust large program. So we should be able to add that future data that's also high resolution to this data, and we'll be able to get more sensitive. But I think what might be even more interesting is when we subtracted the model from the data, and you see that there's sort of this asymmetry to the side here. No matter how we actually, we played with so many inclinations and position angles of this disk and different flaring properties of the disk, and we could not get this asymmetry to go away. It just doesn't make any sense. The asymmetry has to be real. And what I think is interesting is that the streamer, we think, is approaching from large scales here, well, even farther out, but it's actually connecting with the disk somewhere down here in this region at slightly larger radii. So that might be evidence that it's connecting here and then pushing material around to the other side where it's building up in this sort of azimuthal zone. So dust might be bunching up both radially and azimuthally. So the asymmetry is sort of a minor point now, but I don't know that we have any models that predict how this material should interact with the small scale dust emission, but it's certainly something we need to take into account. And there's this little tantalizing hint for why it could be important with this asymmetry here.
Yeah, thank you. And also just a quick comment. I think there may be a analogy in galaxy formation, although the physical scale is vastly different. But if you think about cold accretion and filamentary structure in terms of the growth, it almost seems that you also have a very similar situation here where you see streamers flowing in instead of just the traditionally oversimplified picture of a spherical infall.
Absolutely.
Yeah, it's very, very interesting. Yeah.
Okay, Richard.
Yeah, is there anything known observationally about the possible relationship between magnetic field morphology and the streamers you're talking about?
Not yet. That's something I'm eagerly waiting for or planning to apply for. In particular with this class 0 streamer. It's on a lot larger size scale compared to the class 1 streamer. So I think that with the class 0 streamer, it would be possible to use SOFIA and the Hawk Plus instrument with the E band to get maybe the connection to the core. So it'd be interesting to see if, even if there's just a few vectors around this area, but is it consistent with vectors that might be further over here and connecting to the core? However, with the class 1 streamer, we don't have as much dust present here. So it's going to be harder to try to get polarization there, although I'd like to figure out how in the future. I don't know of any Zeeman molecules that are actually found in the streamer, although we haven't looked for them yet. So one option here, since we don't have so much dust, would be a pilot study to try to figure out if there's molecules that we can use to get Zeeman splitting, and then try to constrain the magnetic field from that. But first, I think we have to prove that those exist before we go super deep to try to get the Zeeman. Definitely on my mind, though.
Okay, so Leslie.
Hey, thanks, Dom. Nice talk. Sophia may be a little, Hawk Plus might not be sensitive for that low surface brightness, but I think we could play with, might be better later when it has more sensitivity. My question though is kind of similar, which is, as you know, Sarah Satovoy's image, polarization image of IRS-63 has this interesting effect where the inner region looks like scattering and the outer region may be magnetic fields. Have you overplotted that on some of your diagrams because it looks like it happens at that sort of at the ice dust ring scale? You should actually, the scale you were just kind of showing what the excess continuum is. Yeah, on that scale, about the inner circle ellipse there, the second ellipse, I guess, is about where it's dominated by scattering, and then outside of that, it's dominated by probably magnetic field or something else.
Yeah, good point. I guess also that doesn't surprise me too much because Sarah's the resolution of Sarah's data is also around 100 AU. So it's like 3 or 4 beams across the disk. But then what I also found was that in this disk, anything within about 20 AU looked like it was probably optically thick based on the in-band spectral index measurements. So I think the inner part is optically thick. So that would naturally sort of explain like why we start to see scattering there. But
not necessarily, because scattering can also flip the polarization. So it's not you have to model and play with it more carefully.
Yeah, exactly. There's a lot of cool stuff to be done with this. Yeah, not something I thought about, but yeah, good point.
Okay, looks like we've asked a lot of questions. So if no more questions, let's give Dom another round of virtual applause. Thank you, Dom, for an excellent talk. And of course, thank you for staying up so late to keep the talk.
Okay, thanks for having me. It was really fun getting to, I don't know, present back at home.
Welcome back. And now, go. You can go to bed now.
Yeah. Okay. Bye-bye.
Bye.
Bye.